All right, let's talk tectonics. The forces that shift continents and build mountains from the seafloor can be pretty challenging topics on your geography exam. So in this explainer, we're going to break down the exact science you need to know to absolutely nail those questions.
We're actually going to use a 2025 exam paper as our guide today. But look, the goal here is not to just memorize answers. It's about getting a really solid grasp of the geology behind things like submarine volcanoes, earthquakes, and disaster risk. That way, you can apply that knowledge to any question they throw at you.
So, first up, the transform boundary. This is where two massive tectonic plates are literally grinding past each other. And yeah, this is the engine that drives some of the world's most infamous fault lines and the massive earthquakes they're known for. Okay, so this diagram really lays it all out. Just picture two huge continental plates trying to slide past one another. But the thing is, the movement isn't smooth at all. There's so much friction along the fault line that they get stuck, they lock up. All the while, the plates are still trying to move, so this incredible geological stress just builds and builds. Eventually, that stress just has to go somewhere. It becomes too much, and it's released in a sudden, violent snap. And that snap, that's the earthquake.
So, to boil it down for your exam answer, it's pretty straightforward. A transform plate boundary is where plates slide horizontally past one another. And the key result of that? You get fault lines, and all that stored up energy gets released as earthquakes. Simple as that.
Now, while transform boundaries are all about that destructive energy, other plate interactions are actually incredible forces of creation. So let's dive under the waves and see how brand new land is literally born from the ocean floor in the form of submarine volcanoes.
You can think of the creation of an undersea volcano happening in four main stages. It all starts deep in the mantle when rock begins to melt. Then, that molten rock, we call it magma, starts rising up toward the surface. Next up is the main event, the eruption, where it finally breaks through the seafloor. And finally, you have accumulation, where all that lava cools and hardens, building a brand new mountain layer by layer.
So here's exactly how it plays out at an oceanic convergent boundary. You have one plate diving or subducting underneath another one. As it goes down, it drags water with it deep into the super hot mantle. Now, you'd think water would cool things down, but it actually does the opposite. It lowers the melting point of the rock around it, creating magma. And because this magma is less dense than the rock surrounding it, it starts to rise, finding weaknesses in the crust. Eventually, it erupts onto the freezing cold ocean floor, and that lava cools and solidifies almost instantly. Over thousands and thousands of eruptions, these layers just keep building up until you have a massive underwater mountain, a submarine volcano.
You know, the shaking from an earthquake is really just the start of the problem. Some of the worst damage actually comes from the secondary effects. And now we're going to look at one of the most terrifying of all, liquefaction. That's when solid ground can suddenly start acting like a liquid.
This image really shows you what we're talking about. Liquefaction happens in soil that's loose and saturated with water. When an earthquake hits, the intense shaking ramps up the water pressure between all the little soil particles, basically forcing them apart. And just for a moment, the solid ground completely loses its strength and behaves like a fluid. Of course, anything built on top of it, buildings, bridges, roads, loses its foundation and just starts to sink or tilt over.
And the chain reaction from there is just absolutely catastrophic. You've got buildings sinking and collapsing because their foundations have turned to mush. Underground, all the crucial infrastructure like water pipes and power lines just snap, crippling the whole city. And that, in turn, paralyzes any rescue efforts, right? Roads become impassable, emergency services can't get through. So liquefaction doesn't just add to the damage, it literally multiplies it.
So, this all leads us to a classic kind of evaluation question you'll see on exams. When a volcano erupts, what's the biggest factor in how bad the disaster is? Is it the raw, uncontrollable power of the volcano itself? Or is it us, the human factor, how prepared we are?
So you can see the two sides of the argument here. On one side, you've got the raw geology, the nature of the magma itself. On the other, you have our preparedness, everything we do to try and lessen the impact. To figure out which is the main factor, we've got to weigh them both. Let's start with the volcano.
The magma's chemical makeup is really the starting point for everything. If you have high silica magma, it's thick and sticky, kind of like honey. It drops volcanic gases, which builds up enormous pressure, and that leads to these catastrophic explosive eruptions. But if you have low silica magma, it's much more fluid and runny. The gases can escape easily, and you get what are called effusive eruptions, where the lava just flows out more gently. It's still dangerous, but way less explosive.
And the source material really hits the nail on the head with this quote: The chemistry of the magma sets the baseline for the hazard. It determines the absolute potential for destruction before we even start talking about anything humans can do.
But of course, that potential for disaster isn't the whole story. The other side of the coin is our preparedness shield, everything we can do to reduce that risk. This really comes down to three key things: hazard mapping, so we know not to build in the most dangerous places; monitoring and warning systems to give people precious time to get to safety; and public education, making sure everyone knows exactly what to do when a warning comes.
So, how do we weigh these for our evaluation? Well, think of it like this. The magma's nature is uncontrollable. It just sets the potential for how bad things could be. Human preparedness, on the other hand, is something we can actively manage. It's what determines the actual outcome for people and communities. A really well-prepared town could face a huge eruption and come out okay, while an unprepared town could be devastated by a much smaller one. So while the magma is the source of the danger, you can argue that human preparedness is the main factor that determines the level of the disaster.
And this really leaves us with a huge question for the future. We live on a dynamic, restless planet. These tectonic forces aren't going anywhere. So the ultimate challenge isn't just getting better at predicting these events, but getting much better at preparing for them. As we go forward, the real question is how we'll strike that crucial balance between the science of prediction and the art of preparation.